Hello students, welcome to EPG Pathshala. I am Dr. Nasir Iqbal from Department of Physics, University of Kashmir, Srinagar. Today we are going to talk on the module Photometry under the paper of Astronomy and Astrophysics. After completing this module, the students will be able to learn about the basics of photometry, why photometry is important, and what information it provides about the celestial source that is under observation, to know about the basics of terminology used in the subject of photometry, to learn the methods of photometry and point spread functions. So let's have an introduction to the photometry. The most important information that we receive about the celestial object is the amount of energy which we called as a flux in the form of electromagnetic radiation. The science of measuring flux from celestial objects is called photometry. This is an efficient way of carrying out the brightness measurements of light from astronomical objects, and therefore it plays a key role for the characterization of an astrophysical target. Our eyes does not respond equally to all wavelengths of visible light. Photometry accounts this by weighing the power measured at each wavelength with the sensitivity of eye at the wavelength. Power at each wavelength is weighed by using luminosity function. This luminosity function differs from radiometry, in which the radiant energy, including the light, is measured in terms of unweighed absolute power. For example, the eye is more sensitive to green light than to red. This means that green source will be more luminous than a red source, and both having the same radiant flux. Radiant energy as a light source puts out very few lumens, as it carries most of the energy in the infrared with dim glow in the visible, and thus outside the visible spectrum it does not contribute to photometric quantities at all. Photometry measures many observable parameters and helps us to obtain the information and many conclusions, like to detect and see the presence of a source, to look for the apparent brightness of a source, which can be used for calculating its luminosity, to see the morphology of the sources which characterize the type of the object, whether it can be considered to be a point source or even an extended one, to look for the spatial energy distribution of the source, and to see that how this distribution allows to see the characterization of the all important radiation components in the system, to see the color characteristic temperature of a star, the stellar population in a galaxy and others, to see the temporal variability of the source, and see that how it can be investigated with many repeated kinds of observations. The CCD photometry is used to obtain the light curves of many faint objects. Due to the interaction of light with the atoms and molecules in the object, the flux is often quite irregular on small wavelength scales. These irregularities in the flux as a function of wavelength can tell us a lot about the object, what is made up of, how the object is moving, how the object is rotating, how the presence and ionization of the material in the object is there. The observation of these irregularities is actually called the science of spectroscopy. A combination of good wavelength resolution that is spectroscopy, and good flux calibration, that is photometry, also to be referred as spectrophotometry. The spectrophotometry is used to obtain the distribution of the celestial objects. Spectrophotometry of an object contains more information than the photometric scan of the same object in same wavelength range. Given this fact, still one prefers to do low wavelength resolution photometry rather than higher resolution spectrophotometry because it is much easier to make photometric observations of faint objects than to make spectroscopic observations of the same object. Also, the equipment required for CCD imaging photometry is cheaper and simpler than that needed for spectroscopy. We also have to speak about the magnitude scales in reference to the photometry of the stars. Photometry is concerned with brightness measurement of electromagnetic radiation from various astronomical sources. Measurements of a star's brightness are usually obtained within a limited frequency range in the photometric band and are therefore more directly linked to the flux density. Since at infrared the measured flux densities of stars are often weak, especially at infrared and radio wavelengths where the photons are not so energetic. The flux density is sometimes expressed in Jansky. However, the basic unit of astronomical photometry is in terms of the magnitude, and astronomers measure the visible brightness of stars in terms of the magnitude from the very ancient times, originating from the earliest known astronomical catalogues. An astronomical catalogue of stars is divided into 6 classes, with brightness 1 being the first class and the faintest one the 6th class. It was Norman Pogson who very earlier in 1856 proposed a mathematical law such that the logarithmic scale approximately agrees with these measurement scales, that is, the magnitude related to logarithmic of the diameter of the minimum size of the telescope to see the star, which we called as actually the limiting magnitude. From very simple calculations, we show that the limiting magnitude of the star is given by the equation that ml, if it represents the limiting magnitude, is equivalent to 16.8 plus 5 logarithmic the distance, where d is not actually the distance but d refers as the diameter of the objective in meters. So it was then generally decided to express the magnitude directly in terms of the flux coming from the star, defined by the equation m is minus 2.5 logarithmic f by f naught, where f naught is fixed as reference to standard stars. These standard stars are chosen such that they are non-variable and their magnitude is set to be 0. The larger magnitude means the fainter sources. So we refer many things under this discussion in terms of different terminologies, and some frequently terms encountered while studying the photometry are as: the first one is the absolute magnitude. The absolute magnitude has a distance dependence of brightness. It gives the intrinsic amount of the brightness put out by the source. It is equal to the apparent magnitude that the source situated at a standard distance of 10 parsec. Absolute magnitude satisfies the relation given by m minus m, one small m and the other capital M, is equal to 5 logarithmic to some distance minus 5, where rho is the distance from the source in parsecs, which is an astronomical unit. If the interstellar magnitude adds a magnitude to the apparent magnitude, then same amount should also be added to the right of the above equation. The other magnitude that we discuss is the apparent magnitude. The apparent magnitude is the brightness of the star, and it's defined by the formula m is equal to minus 2.5 logarithmic f by f naught. Then one more technical term to be used is the Balmer decrement measures. This is the discontinuity which takes place in the near ultraviolet stellar spectrum at the end of the hydrogen-Balmer series or hydrogen-Balmer absorption, which is of a special feature. This is sensitive to temperature as well as gravity. Therefore, different photometric include monitoring on either side of the discontinuity to determine the jump in energy forms or jump in energy terms or the decrement value. In UV by systems, the change, that is the UV and the V minus B, correlates with Balmer decremental, and this is denoted by the special symbol C1. The other technical term to be used is the volumetric magnitude. The volumetric magnitude is the total power of the source integrated over all wavelengths. It therefore goes beyond the magnitude at some particular wavelength, and this must be added to the visual magnitude and its value in general magnitude. We also refer one class, that is the brightness. In case of points like sources, stars' brightness is closely associated with the apparent magnitude of the star. One more technical term to be used is the effective temperature. Effective temperature is used to characterize the overall emission of a unit area of a radiation source. The effective temperature is that of Planckian radiation field having same integrated emission per unit area. Extinction. The light from stars first passes through the absorbing or scattering medium like Earth's atmosphere as well as interstellar medium and then reach the detector. During the passage, the intensity of emitted light decreases. The extinction is the coefficient that depends on the medium and the wavelength of the transmission. For Earth's atmosphere, the extinction coefficient at the observation wavelength is denoted by K, while as for interstellar medium, instead of K, the symbol A is used. We talk about the flux also, which measures the energy of the radiation field passing per unit area. This is more suitable unit than magnitude for general physical classes. Luminosity. Luminosity is a measure of the radiative power of a source. It relates to the entire output and therefore is related to the absolute volumetric magnitude, defined by volumetric magnitude is equal to 4.75 minus 2.5 logarithmic of L by L star, where L star represents the solar luminosity. We also talk about the standard magnitude. Apparent magnitude is too imprecise for science to be used. Over the last few decades, the apparent magnitude system is more precisely defined that allows different workers to use their local measurement and disadvantages to convert a general recognizable scale, that is standard visual magnitude. Then one more important thing is to talk about the standard star. Magnitude is defined in reference to the standard star that is usually bright and well known, such as, for example, Vega or the then primary standards of the UBV system. Methods of photometry. So what are the various methods which are used to do the photometry? We know the basic task of photometry is to gather the light in a telescope from the star and extract the detected signal. The past measurements were based on eye estimates, and even today, all photometric measurements depend finally on the judgment of eye. With the help of instruments, we can aid the judgment very much by limiting the point to be decided whether two lights as seen are exactly the same or they are not, or else making the decision dependent on the visibility or non-visibility of some appearance. Even in some cases, the unaided eye is quite as good as any photometric instrument. In the sequence method, the observer only arranges the stars he is comparing in the order of their brightness by taking care that the star in each sequence list are nearly at the same altitude and seen under equally favorable circumstances. Then he arranges a second sequence by taking care such that some of the stars that were in the first should be included in it. Likewise, he makes the third, the fourth, and so on. Lastly, a list is formed from these sequences that include all the stars arranged in the order of brightness. However, this method does not give the number by which the light of the brightest exceeds that of the faintest one. While talking about the instrumental details of these telescopes, in instrument method for the measurement, these are done by making the star to disappear for decreasing its light in some measurable way. This method is also called the method of extinctions. The light of the star is made to be equal to some other standard light by decreasing the brightness of the star, and is made to be equal to some other standard light by decreasing the brightness of the star or of the standard in some known radio until they are perfectly equalized. This includes the photometers working on the principle of limiting apertures. The telescope is fitted such that the available aperture of the objective glass can be diminished whenever we want, and the observation consists in determining with what area of the object glass the star is first visible. Method for this star has difficulty of constant errors relative to glass thick in the middle of the lens comes, and diffraction from very small aperture makes the image of the star to be large and to diffuse. Now we also talk about the aperture photometry. The aperture photometry is done by measuring the brightness of a star using the aperture to collect the counts from the star. In this case, the pixel values are summed within a circular region centered on the earth or centered on the object that is a star, including light from the star as well as light from the sky. The latter is corrected by measuring the sky's brightness within an annular region surrounding the central aperture. Therefore, subtracting the sky measurement from the star plus sky measurement then gives or yields the target signal. This can be taken continuously in consecutively using multiple aperture instruments. So the image generators, they use the software apertures which can be optimized in number of ways to improve the photometric measurements and extract the clean signal. Aperture focus on the target can be achieved. We can adapt the size and the shape of the aperture to that individual object. The background and disturbance can be reduced by reducing the aperture size. The clean region of the sky can be used that represents the best background at the position of the target. The aperture geometry can be used to investigate the impact of the selected apertures on the photometric measurements. We can recognize the uncertainties due to other sources or instrumental effects in the image. We have one important also here to talk about the wedge photometer. In this method, the extension is produced by a dark wedge neutral tinted glass of 6 inches long, quarter of an inch wide, and at the thick end cuts of light. In the pre-chart, for the wedge is placed close to the eye at the eye hole of the eyepiece. In some other forms, it is placed at the principal focus of the object glasses, where micrometer wires would be put in observation. The wedge is pushed promptly until the star just disappears, and a graduation on the edge of the slider is read. The great simplicity of the instrument commends it, and if the wedge is a good one of the really neutral glasses, the results are remarkably good. These observations are, however, very trying to the eyes on the account of the staining to keep a girl in sight of an object just as it is becoming invisible. The constant of the wedge must be carefully determined in the laboratory. That is, what wavelength or what length of the wedge corresponds to a diminution of the light of a star by just one magnitude. It is convenient to have the slider graduated into reaches or millimeters on the one edge and magnitudes of the star. The Uranometria Nova Oxonicis is a catalogue of the magnitude of the naked eye stars to the number of 2784 between the pole and the 10 degrees south declination, observed with an instrument of this kind by Professor Pritchard and published in long back in 1885. The image directors use the softwares Apertures, which can be optimized in number of ways to improve the photometric measurements and extract the clean signal. Like how it can be done? Accurate focus on the target can be achieved. We can adopt the size and the shape of the aperture to be individual object. The background disturbance can be reduced by reducing the aperture size. The green region of the sky can be used that represents the best background at the position of the target. The aperture geometry can be used to investigate the impact of the selected apertures on the photometric measurement. We can recognize the uncertainties due to other sources or instrumental effects in the image. So, let's talk about the point separate function. Real stars are not precisely point-like. They have finite angular size. However, the angular size of almost every star in the sky is too small than the diffraction limit of our optical telescopes. So, we can treat stars as unresolved points. The stellar profiles are centrally concentrated and star counts fall off with increasing distance from the star center. The point separate function. In telescopes, the dominated source of the point separated function is caused by the passage of starlight through the Earth's turbulent atmosphere. This makes images of the stars are like roundish dishes of light. So the stars are like roundish discs of light. The shape of PSF is very complicated. It can be approximated by a central Gaussian core and a large hollow approximated by power law. The angular size of the PSF can be approximated by the full width at half maximum, that is the diameter, where the flux falls to half of its central value. More centrally concentrated PSF is higher the sensitivity to detect faint stars will be. to resolve closely spaced stars. Poor telescope focusing and tracking error leads to degradation of the PSF. Therefore, should be taken care of with good observing techniques. It may be noted that in telescopic optics, we are bound to determine the shape of the PSF, then the images are diffraction limited and appears as airy discs surrounded by concentric minima and maxima. The size of the central disk depends on the wavelength of the light and on the diameter of the object mirror of the telescope. D. Two equally bright stars are resolved if they are separated by at least the size of the airy disk, which is given by the distance from the center to the first minimum defined by the relation this theta is equal to 1.22 times lambda by d, where lambda is the wavelength and d is the diameter of the primary mirror. So, students, let us see what we are going to learn in this module. As we talked about the subject of the photometry, and photometry, as we have said that photometry plays an important role in the observations of all the celestial objects, whether it can be a star, it can be a bright star, it can be a faint star, it can be a galaxy, it can be a cluster of stars, or it can be a cluster of galaxies. So we can talk about what we are expected to learn now, the basic introduction to the science of photometry, and to know about the magnitude scales of the stars, as magnitude scales of the stars are related with the first class magnitude, the second one, followed by the third one, the fourth one, and the fifth one, and then the sixth and the seventh one. We have said that the first class star magnitudes are much brighter, 100% brighter than the seventh class stars. So then we discussed about some basic terminology that's used here, and we talked about few methods that are used for elaborating the phenomena of photometry. We talked about the aperture photometry, we talked about the wedge photometry, we talked about a PSF, that is the point spread function, which is important in knowing about the photometry properties or the photometry of any celestial object. Thank you.